Welcome to everybody on board. And Russell, can I ask you to do the honors, please?
Sure, Donnie. Sorry about that. Okay, no, clearly videos are off. So thank you for that, Donnie. And apologies to everyone. We are using the same platform as the conference which was going on previously and ran over time. So apologies for keeping you all holding on. We are very fortunate tonight to have a very professional lady, a very well-experienced lady talking to us about the ore and metal accounting processes.
Russell, speak up, please. Russell, I hear background noises. Maybe you're there.
Can you hear me now, Danny?
No, 100%.
Okay, no problem. Sorry, I took my earbuds out. Yeah, sorry. So the presentation tonight is around the ore and metal accounting processes and the tracking of value through the entire chain from mining or from ore in the ground through to the feed to the plant. Monica is a postdoctoral fellow at the Wits Mining Institute. She holds a PhD in mining engineering, an MSc in mining engineering, and a GDE in mining engineering, all from the University of Wits. And her first degree was in geomatic engineering. And Monica, one day you're gonna have to tell me what that is, from the Kwame Nkrumah University of Science and Technology, which I assume is West Africa. Monica has published in journals and presented a number of conferences and workshops, both locally and internationally. Her work has been recognized and selected by the Golden Key International Honor Institute. She's worked as a lecturer and a tutor in the field of engineering survey and mining engineering laboratory related subjects at WITS. Prior to academic pursuits and qualifications, she worked as a surveyor in surface mining, land survey and aerial survey. She's a member of the Institute. Monica, I'll hand it over to you. Thank you.
Thank you very much for the introduction. I think I'll zoom straight into the presentation. Let me share. There you go. All right. So can you all confirm if you can see my screen?
We can see it, Monica. Thank you.
Thank you. All right. So a very good evening to everyone once again. And I would like to thank the members of SAIMM and all the ladies and gents who have put this opportunity together for me to present some of the aspects of the work that I have done in my PhD at the Wits University Digimine. The topic of the presentation is time and spatial tracking of metal content from in-situ to plant entry, a digital mining technology. A digital mining technology approach. All right, so I've already been introduced, so I think I wouldn't talk much about myself. Just to give you an idea of the content of the presentation, the outline will cover an introduction where I will try to situate the project in the context of a platinum mining with the surface mechanized mine in mind. I'll then take you through the objectives, the methodology, the research questions that we considered in the thesis. This will be followed by some aspects of the critical review in terms of literature that was conducted as part of the study. These are your software options for mine planning and reconciliation, or tracking technologies that was tested in the past, and the new technology we tested in the study, known as the microdot technology. I'll then take you through a case study scenario for material tracking with measuring points, followed by the conceptual framework developed as part of the study. An example is a dashboard for a productive mine that will be demonstrated. The presentation ends with conclusions and recommendations. So basically, the study aimed at developing an implementation strategy to a long-standing problem in mines where the metal of interest that is finally produced is different from what is estimated and planned. And this problem has been tackled severally with particular reference to a mineral resource evaluation perspective. So our thinking philosophy to address the problem was to use sensor-based technologies where applicable to measure, monitor, and track ore from its fundamental in-situ stage through measuring points until the product is formed. So for the purpose of context, I would use this PGM diagram you see on your screen, value chain as an example. We know our PGMs are primarily recovered from both open pits and underground mining from polymetallic sulfide ores. PGM mines are mostly integrated from mining to refining and will therefore maintain considerable processing assets that will produce refined PGMs and byproducts. The diagram displayed on the screen, we have grouped the mining and refining PGMs into 5 different activities with specific outputs. Activities including mining, which involves underground or surface mine of the ore. The valuable mineral within the ore is then liberated by crushing and milling processes, then concentrated using flotation cells. The successive stages are to further refine the quality of the product and extract byproducts. These include smelting of dry ore in an electric arc furnace to remove sulfur, for example, for potential sulfuric acid production, followed by extraction of base metals using magnetic separation from the PGMs concentrate. So we believed that our thinking philosophy in terms of using sensor-based technologies to track these activities will contribute to a good metal accounting governance structure. Objectives outlined in the study was to investigate the possible use of the microdot technology as a viable ore tracking solution. Objective 2 is to spatially analyze the ore flow from the mine to mill toward a metal accounting and reconciliation system. You can call it the dashboard concept. The third objective was to determine specific technologies to measure, track production information, such as your volume, mass, grade, density, and fragmentation. Now, all these 3 objectives is what we've summarized in the diagram of the screen. Primarily, it consists of systems and technologies that would enable data to be transferred in a 2-way path into a control room for further processing and analysis. So the research question seeks to give an answer to the question, which digital technologies do we combine to enable us effectively track ore throughout the production value chain for better metal accounting and reconciliation? Methodology employed is in 6 stages. The literature review on various topics that embody metal accounting and reconciliation. Stage 2 was a site visit to understand existing measuring systems and protocols. Stage 3 is a laboratory testing of the microdot technology. Stages 4 to 6 is just a conceptual solution for ore flow modeling and real-time material tracking and inventory tracking. We believe the conceptual solution should serve as a guide for implementing a successful material tracking and accounting system. Expected outcome of the study is to enable particular ore types passing through specific measuring points to be linked to their specific sources from surface or underground. This should enable problem areas in a mine to be identified so that immediate actions can be focused on these problem areas. So we conducted a review of 4 different mining and reconciliation software options at the time. The reason for these choices was because there was partnership between Digimine and these software companies at the time. We looked at the Snowden's reconciler system, which is a web-based system. basically gives users the requisite tools to use to capture accurate data, validate the data from relevant sources, and enable the numbers for all tracking and reconciliation to be verified. We also looked at Deswick, which has developed several software suites for planning, geology, and survey. The software solutions, although not integrated in a single dashboard, can be used in various mining methods and for various metal commodities. We also looked at Maptek's MRT system that has functionalities for real-time material tracking and compliance to plan measurements. A leading software planning solution that we discussed was also MineRP software, which has developed spatial platform that integrates all mining technical data onto a central dashboard, and therefore the status of the mining activity can be viewed in a 3D single model in real time. Other activities such as your mine design, scheduling, asset management can all be done in this single dashboard. Still on some of the relevant technologies that were tested on the mines in the past, we looked at the work that was done as part of the Deep Mine and Future Mine projects in South Africa. What you see on your screen is just a Nikon D200 camera system and a Canadian WebTrack software that was installed for the continuous real-time particle distribution of material flowing on a conveyor belt. We also looked at the research that was conducted by JKMRC, and they demonstrated the use of RFID technology to track all parcels throughout the mining process. The material is tagged at the source using markers representing volumes of ore or waste, and later detected as it flows through the system, or not detected if it goes to the waste dump. In cases where the tagged material is sent to a long-term stockpile, it can later on be detected when it is processed and reconciled back to its source. So the South African example of this technology is the ore track system provided by the RFTAC South Africa, and has been used successfully in several mines, primarily for the prevention of cross-tramming. In terms of the technology that we really tested as part of the study is the microdots veridot system. It's what you currently see on your screen here. It comprises of a self-contained aerosol system. It is transparent in this, as you can see in this image. It is hexagonal shaped, about 1.3 to 1 millimeter in diameter, not very visible to the naked eye. The product is made from nickel and is able to withstand temperatures to a maximum of 1,200 degrees Celsius. The disc sizes, we've already talked about that. Just to bring this into perspective, your microdots are like the size of your pinball tips. The technology has been used very well in various assets tracking industries, particularly in the vehicle parts, vehicle tracking, that uses a vehicle parts using a unique numbering system. These numbers are visible only to magnifying lenses or a UV light. Now, we felt that the following may be possible if the microdot is determined as a viable ore tracking solution. So for example, if microdots are found to be viable, then it's possible to integrate that technology within the mine-to-mill optimization process. This can help in solving all problems, problems of material loss, incorrect routing, similar to what the RFTAC actually does. We also thought that once the ore reaches the surface or stockpile at different locations or directly sent into the mill for processing, the fact that we have these unique identities attached to the ore can enable us to understand discrepancies in terms of quantity and quality estimates. We also looked at the possibility of the technology assisting with better ore accounting and reconciliation, and also for blending and dilution issues. If these unique microdots, for example, is able to link, we are able to link the attributes of the ore to these unique identities. This will enable the processing department to better understand the ore properties of the material that is delivered by the mine in real time and ultimately improve your blending and dilution activities. So this just as a laboratory procedure that we designed for the tests. It's outlined in the figure you see on the screen. We first determine how these microdots are distributed on a sample area. These include testing of the distribution of the microdots over the area, taking basic measurements of the sample. We also immersed the samples into water for 24 hours. And we heated the microdots that we sprayed on these samples up to a maximum of a temperature of 100 degrees Celsius, and that was due to laboratory limitations. We also crushed these samples into coarse and fine samples. This approach was chosen to simulate mining conditions as practically as possible, bearing in mind the laboratory limitations. So basically, these are, before applying these microdots to the samples, the structure of the text in the microdots had to be determined. So we created these thin section cores you see on your screen. And then we were able to view the codes that was embedded in these microdots. That is what you currently see here. And then these are the core samples that we used in the lab. So these samples were taken from the Bushveld igneous complex and was just used for the test. And these are some of the results of the images we got using a very electronic, high visibility electronic microscopes. Some of these results indicated that, yes, the microdots were able to retain the data integrity after we had subjected them to all of these mining conditions that I mentioned in the previous slide. So data integrity was retained irrespective of the type of micro aerosol system we used, whether it was 10,000, 5,000, or 3,000. It was good to actually retain the data integrity. This image depicts the visibility of the microdots on the coarse crushed samples with sizes ranges from 2 centimeters to 3 centimeters. And we were quite glad because we could still see that these microdots did attach to the ore, to the coarse ore, whether crushed or uncrushed, and data integrity was retained. We could actually still read the codes from it. And we did a further screening of the samples into very fine sizes. And what you see on your screen is just the classification of fine sizes that we were able to gain from the lab. The table on the right, on what that you currently see, tells you the results in terms of the visibility of the microdots on the fine sizes. So generally, irrespective of the aerosol system, microdots were still very visible on fines that were 2 millimeters and upwards. In terms of a SWOT analysis that we carried out to assess the strength, weakness, opportunities, and threats of microdots in relation to the RF tags. Although there were a number of strengths identified, data integrity was retained after subjection to heat, water, and crushing. we felt the technology may not be appropriate, maybe for probably your coal industry that experiences spontaneous combustion issues. However, there is a possibility of implementing the technology in the platinum mine, mechanized mine, which is the context that we're really looking at trying to test this technology. So there is still a feeling of a potential for further investigation in a real mine with the technology. So recently we can confirm that at the time we did the test, we hadn't gotten this information, but we can confirm that to some extent, the technology can actually be digitally tracked. And what you're currently seeing in the video playing on your screen are chrome rocks that microdots had been sprayed onto. In a while, you'd see the reader that is attached to the chrome ore to try and determine the DNA of the microdots of that particular rock. There you go. All right. So there is some potential to digitally track these microdots. Again, this other video shows the visibility of the microdots using your UV lights, which you can actually even use your phone to detect. But again, there is still a bit of a concern because how do you integrate? This is not a real mining environment. How do you then integrate this sort of tracking of the microdots in a real mine environment? And so those were the concerns. Those are currently the concerns we've had with the technology. All right, so in terms of your material tracking, now we looked at, how do we, conducting an in-process inventory measurement. This is just a generic mine-to-mill reconciliation process where your measuring points are established for reconciliation purposes. So for example, reconciliation factors that are expressed in terms of percentages are determined between your grade control model and your resource model, for example. The main objective for performing this kind of mine-to-mill reconciliation process is to obtain reliable production figures for the purpose of metal accounting and reporting, and to scrutinize the performance of quantity and quality estimates from between any two measuring points. So for example, between your resource model and your grade control model, for example. And I'll demonstrate just a quick statistical analysis we conducted to help us understand how reliable our measuring estimates are. Like I said, your reconciliation factor calculates or compares the quality and quantity estimates between any two measuring points. For example, in this instance, we looked at between your grade control model and your resource model, and we see a very good linear correlation graphs, and it gives us a confident understanding in terms of how reliable the measuring systems are coming from those two sources. Now, in a typical mine, real mine, remember our thinking philosophy is to have a physical installation of sensor technologies that can measure, track, and monitor the production variables from the source to the plants. So in terms of, this is just a sample case study of installing technologies at your physical measuring point on surface so that we can measure these production variables in real time and report the information into a control room, transmit the data electronically into a control room for data analysis. The diagram you see outlines just the process for conducting reconciliation of measuring your measurement variables at measuring points. is a workflow that is outlines all the specific, production variables that you would consider in your typical production value chain, like your mass, your grade, fragmentation, density, location-based, moisture content, etc. So from the previous slide, we've looked at the identification of your physical measuring points using a mechanized mine for context. Here we simply demonstrate a process for data verification. The way to do this is just to measure the variable of interest, determine the discrepancy in terms of what is planned and expected, and then the risk of that discrepancy can be determined based on the tolerance limits for each measurement variable. This is just a conceptual framework developed for purposes of implementation. I think I would like to focus my discussion on phase 4, where we're looking at the concept of, understanding metrics that speaks to the efficiency of our mining process. So we're thinking that we can actually have this kind of dashboard in place where your key, your key production metrics for monitoring production variables are displayed in your production meetings. So for example, your survey tons versus your track counts can be compared. And then you can also look at your resource versus your stockpile reconciliation graph to understand how reliable your estimates are coming from those sources. We can see a linear correlation in that data, which is an indication that our measuring systems are reliable from both a resource model perspective and actual mining perspective. We also have your rock lab, for example, your QA/QC analysis for grade measurements. Ultimately, we want our grade values to be within your +2 or -2 standard deviation lines. Anything outside that needs to be investigated. We're also looking at your time series graph, which displays your monthly tonnages. There are spikes in that data and indicates some sort of need to further investigate. We also did this discrepancy graph, which compares your survey tons with your milled tons, and your almighty mine call factor, which also gives you an understanding of the efficiency of your entire mining process. This threshold that was introduced as part of a control limit. In order to demonstrate some of the concepts that I mentioned earlier on, this is basically a grade variance map that we created using your production planned grade and actual grade. So we used GIS to enable us understand visually issues of grade variances. So what you currently see is like a planned grade figure that was planned to mine your high grade. So these are just color grades that we created. Your green is denotes your high grade material. Your medium grade material is what is in the middle, and your low grade material is what is displayed as this section. In actual, we can see that there's a bit of shift in terms of what we expected. So in this region, we had a bit of a success story in terms of mining high grades. In the middle portion, it's a different story. And obviously in this part of the area, it's also a totally different story. So these are what we termed grade variance maps. it's a discrepancy that we use to understand or to determine the root causes of discrepancies, for example, in our grade measurements. If it is outside the tolerance, we have to go back to those graphs that we've created to investigate exactly the root cause of these discrepancies. So in conclusion, I think we believe that there's a strong need to physically track production variables from physical measuring points. We've demonstrated that initially. There's a need to think more into employing sensor technologies to enable us to do real-time material tracking in our production value chain. There's a need to define a data verification process to ensure accuracy. We looked at the conceptual framework that was developed as part of the study. We also demonstrated the concept of developing grade variance maps. And this work has been an ongoing project at the Wits Mining Institute, hoping that some of the concepts would be implemented in real mines. I really can't talk about this project without acknowledging the sponsorship we got from Sibanye-Stillwater, a grant supervisor who gave me a hard time, but successfully led this project, Professor Kewood. I can't also leave out my digital mine research group and the entire West School of Mining Engineering and the staff of WMI, where I currently get to do a lot of the work that is associated with this project. I'd like to end the presentation with this research quotes. Research is seeking what everybody else has seen and thinking what nobody else has thought. It's from a Hungarian pharmacologist by the name Albert Zenzkioski. I hope the colleagues of this gentleman will pardon me if I didn't mention his name very well. And that brings me to the end of the presentation. Thank you.
Thank you, Monica. Wow. If I think back to my early days in the mining industry, when us metallurgists didn't trust the miners that they were doing the right thing, we used to send somebody underground with different color washers and see where they ended up, how things have changed. There aren't any questions in the Q&A at the moment. If anyone has questions, please put them in the Q&A box. And then I'll pass them on to Monica. Monica, I'll start things off. Was there a reason why you looked at the microdot technology rather than something obviously a little bigger and probably more expensive, like RFID?
All right. Yeah, thanks for that question. So we were aware that the RFID is a success story. I believe in mines, you look for alternative cost-effective solutions. So yes, the microdots hadn't been tested. And one of the differences that we had indicated from the onset was the fact that microdots could attach to the ore, but to the rock, which was something that RFIDs don't do. So it was curiosity on our side to see if we could, employ this technology for ore tracking. And the fact that it was cost effective, I believe, was something that the mines would have been interested in pursuing. Perhaps if, for example, if we are able to integrate this technology and make it, digitally tractable, and we can successfully incorporate it into the mine-to-mill optimization process, I believe that will be a huge success story for material tracking in real time.
Okay, I think that sort of leads on into the first question that's been posed to you. What is your next step in terms of the production scale trial or proof of concept?
So currently we're thinking of, bringing this technology in a real mine, having realized that we could actually use readers to track the DNAs of the microdots. So currently there are discussions that have been ongoing, just that in a research environment, the pace of work is totally different from in a real mine environment where the pace is much faster. But we have had discussions with the interested stakeholders regarding testing or implementing this technology in a real mine. And so hopefully that should happen soon.
Do you think it would be equally applicable to an open pit, as obviously you're looking at underground at this point, but would it be equally applicable to open pit?
It should be applicable. Look, you'd want to start such a test from a surface mine and then see how it works, and then gradually transfer the technologies and concepts to underground instead of the vice versa. So the right approach, I believe, would be to start it from a surface perspective, get a better understanding of how it works, and then we can gradually extend it to underground.
Fair enough. Next question, the cans of microdots look quite low volume. What are your thoughts on the volume of microdots practical to dispense into mine production volumes of ore?
Wow. Look, well, it depends on the size, or the size of the phase would determine the quantity of, for example, microdot aerosol systems that you would require for a particular phase. I won't be able to give you the details for that, but let me say that we've actually published this work in SAIMM's journal. So the reason for doing those basic measurements of the samples that I displayed on the screen was to give us an idea of how much would, for example, require should we be dealing with a real, a typical phase where we would have to measure the length and breadth and estimate the quantity. So I think I won't want to be very specific, but I believe it would require quite a huge quantity of microdots to really test in a real mine.
Okay. More of a comment, the next one. Nice to see it actually works. A ready fit with digitalization efforts, I guess, into 4IR and all of these things.
Absolutely. That's the real interest, because you want to be able to receive digital information in real time. As the material passes over a conveyor or any transport system, the idea is to be able to transmit data in real time for analysis purpose, so that in real time you actually understand where your ore is and where your waste is, where is the location, what is its grade, what it's how much quantity it's flowing, and all of that.
Okay, another question. Mine-to-mill accounting is much spoken about outside of digital technologies. How effective are current processes? George is looking for a percent accuracy, I guess, which is probably another open-ended question.
It's quite difficult to say, but I think that we are looking at getting into an era of digitalization is the talk of the day, and as much as we can be able to connect our digital processes in the milling process to that of the mining process, then we are able to bridge that gap and fully understand, a mine-to-mill process, so that there are issues of discrepancies can be well understood and explained, in terms of issues of, professionals from both metallurgy and mining can get to understand, the root causes of discrepancies, for example. I don't know if that answer is satisfactory, but it's like you said, it's an open-ended question. It's not like
how long's a piece of string?
That's it.
Yeah. Another question: what scale of tonnage throughput could this system handle? What are you seeing as the sort of limitations on tonnage at this point?
I don't think it's also, I don't think it's a straightforward answer. Look, there is really no limit at this point. And yeah, in terms of there's not exactly a specific limit in terms of the tonnage that this can handle. So for example, if you have a 150-ton truck and you have microdots, on the content of that truck, I think that's possible. I don't know if that answers the question. Perhaps when we have managed to implement the technology, in the real mine environment, we'll get a fair or a better understanding in terms of, and be able to speak to specific quantities. But as it is now, the testing was done on a very small scale basis, just to understand what, issues of its ability to withstand your typical harsh mining conditions. So once we translate or transfer that into a real mining environment, then we will be able to give specific answers in terms of quantities.
I guess your tonnage throughput kind of almost comes back to a bit of sampling theory, where you need to make sure that you've got sufficient microdots reporting to the right stream, and that there are enough of them to be able to be read. So your analysis or your reading of the microdots becomes problematic if they're too far dispersed.
I believe so. I believe so. Yes, I want to agree with your inputs.
Okay, another question about the microdots and how far they can go down the process. Is it possible to read the microdots after milling? And a follow-on, at what point do the microdots stop being effective in the beneficiation process?
So it's like I mentioned earlier on, this is still an ongoing study. We haven't tested it in the beneficiation process yet. So if you remember the topic, it was from phase to plant entry. So in terms of, I won't be able to say that, but we are aware that there's a possibility of its, withstanding your milling process. Look, temperatures, we currently know from the MS datasheet information that we could actually withstand heat temperatures as high as 1,200. So there's a bit of, how do you call it, optimism in terms of, using extending it in the beneficiation process. So yes, that's it.
It's temperature resilience, but also its mechanical resilience in terms of withstanding milling. Okay, the next question: through which mechanism does the microdot attach to the ore, and up to when does it remain attached? Have you considered microdots segregating in large PSD ores?
So your microdots, it actually it attaches. If you saw the samples that let me just scroll back to those slides. It attaches very well. because it has this sort of watering, a sticky substance that is in the aerosol system. So once you spray it on these samples, it attaches.
So there's some kind of a sticky substrate that it comes suspended in.
Yes. So you see, it sticks directly onto the rock particles. So in terms of it attaching, yes, it attaches very well.
So does
I don't know if that
substrate still withstand 1200 degrees, or is it just the microdot that withstands 1200 degrees?
It's the microdot that withstands temperatures as high as 1200 degrees Celsius. Yes.
Okay, so it would disengage at some point.
I believe so. So if the temperatures are above that, then you wouldn't be able to see them again.
Okay. Okay. Well, Monica, that's all the questions. Thank you for that. That's some fascinating work that you're doing, and we wish you good luck with the next phase of it.
Thank you very much. Thank you.
I'm going to hand back to Dani.
I say thank you, Russell, and thank you, Monica. Thank you very much for your very interesting presentation. I believe the mining community will be very thankful for this interesting step in the digitizing of the mining process. Also then, please accept a delivery from the SAIMM office to receive a valued pin set that I can't show you now, to further your valid research output. SAIMM Johannesburg Branch would like to thank your sponsor, yourself, and the SAIMM attendees, members tonight. Wishing you a very, very nice evening further. So, Monica, again, thank you very much for a very interesting presentation. It's really, it's as I seen it, it's a great step to the fore, and it's actually heartwarming to see that a lady in mining is taking this huge step. Thank you very much, and it's really much appreciated from our side.
Thank you very much for the opportunity, and thanks to all the participants for your attendance and your time.
It's a great pleasure, and thank you for the attendance, for the members. While the members are online now, please make yourself available for the AGM in 2 months' time, July, so that we can get ourselves in strength again, and we can go on with the good work. Thank you very much, guys. Have a nice evening.
Thank you.
Thank you, guys. Bye.